Hi guys, welcome to lesson 9.7, linear, quadratic, and exponential models. And our objective for the day is to choose either a linear, a quadratic, or an exponential model for our data. All right. So our first problem, we are starting off with just choosing a model by graphing. So up at the top of the page there, we've got a couple examples of linear, a quadratic, and exponential graphs, just to give you a reminder of what those three look like and what form their equations are going to be in. So we start off by graphing each of our points. So Ms. Zirzo will put a point at 0, 0, at 1, 1, and at negative 1, negative 0.5, and 2, 3. And the shape of that graph kind of sort of looks like that little bit of a curve, so that is going to be an exponential graph. Number 2, we start off, we're going to graph each of our points. So we're at negative 2, 11, so it's going to be a little above our graph, but that's all right. Negative 1, 5, 0, 3, and 1, 5. So we've got kind of a U shape in the middle there, so that looks like the quadratic graphs that we have been working with for the last 2 chapters. So that's going to be quadratic. Next up, we've got letter C, plot the points 0, 1, 1, 2, 2, 4, 3, 8. All right, and for that one, that certainly looks like an exponential, and it is. Letter D is plot, and we're going to start with plotting our points again. We have negative 2, 5, negative 1, 7, 0, 9, and 1, 11. So it'll be a little bit off the graph. That is a straight line, linear relationship, so that is a linear graph. And our last one, again, let's graph our points. Negative 1, 2, 0, 0, 1, 2, and 2, 8. So again, we have that U shape. It's going to be a quadratic because that is a parabola. Moving on to problem 2, choosing a model using differences or ratios. So there are a couple different tricks that we can use if we've got just our data in a data table. If we've got a linear situation, we're going to have a common difference for both x and y. We're going to be adding the same amount every single time. So on the left-hand side, our x values, we are increasing by 1. Our y values are increasing by 3. This is a linear graph. The slope is 3. Okay. An exponential graph. We are adding 1 for each x value, but we are multiplying by a common factor for our y values. In this case, we are multiplying by 2 every single time. That's going to be an exponential graph. And for a quadratic, we have our common ratio or common difference for our x values. We're adding the same number every time. But for quadratics, the first difference, which would make us look for a linear equation, it's not. So we try our second difference. So we take the difference between our differences.
Difference between difference.
Right.
So let's just break it down.
As we go from 1 to negative 1, we are adding 2. To go from negative 1 to positive 1, we're adding 2. To go from 1 to 7, we're adding 6.
No longer linear.
Not linear. We're going from 7 to 17, we're adding 10. So that's not going to be linear. Our first differences are not the same.
It's not working here either.
And we're not multiplying by the same factor, so there's something else going on here. So we use our second differences. So the difference between 2 and 2.
It was a negative 2.
Oh, that was a negative 2? Okay.
Yeah, sorry.
So we had a negative 2. So the difference between negative 2 and positive 2 is we're adding 4. To go from positive 2 to positive 6, we're adding 4. And to go from positive 6 to positive 10, we're adding 4. So our second difference is going to be common. That means it's quadratic. And the rule basically goes, for each level of exponents you have, you can check that level of difference. So a cubic would have the third difference would be the same to the x power. So for quadratic, we're looking for the second difference. Linear, we're looking for the first difference. So let's take a look at problem A. We are increasing our x values by 1 every single time. Now as we look at our y values, we're adding 0.5, we're adding 1. Okay, so we're not going to be linear. All right, well, our second difference, we're going, we've got a 0.5, a 1, and a 2, so it's not quadratic. Are we multiplying by the same value to go from each step? So to go from 0.5 to 1, what did we need to multiply by? A positive 2. Well, 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. So this is going to be an exponential because we are multiplying by 2 every single time. All right, letter B. Our x values, we are increasing by 1 every single time. We are adding 1. So let's take a look at those y values. From 0 to 0.25, we add 0.25. From 0.25 to 1 is adding 0.75. We're adding 1.25 and 1.75.
Not linear.
It's not linear. Our first difference is not the same. We're not multiplying, it doesn't look like. So let's try our second difference. We're adding 0.5. We're adding 0.5. We're adding 0.5.
I see a second difference.
I see a second difference that's the same. So this is going to be a quadratic function. Our third problem, again, we are adding 1 every single time on our x-axis. On our y-axis, we are adding 4. We're adding 4. We're adding 4. And we are adding 4. So we have a linear relationship. Our first difference is common. Next up, problem number 3, modeling real-world data. This table shows the annual income of a small theater company. Which type of function best models the data? And we want to write an equation to model that data. So let's just first look and see if we can figure out what's happening. To go from 18,255 to 18,735, we are adding $480. Let's see if that pattern holds true. As we take our next step, again, we're adding $480. We're adding $480. And we're adding $480. So this is going to be a linear relationship. So if we think back to, what chapter was that? 5? Chapter 5, when we were doing linears, our slope, or our rate of change, is the change in y over the change in x. So 480x plus, what's our starting point? When x is 0, y is $18,255. So that would be our equation to model it. And we can always double check that by plugging in a couple of these values and seeing if the equation works, which we know it will.
Hey, Mr. Bolin, what's this?
Oh, yeah, hey. So we would like to invite you to be our guest as we witness a tale as old as time. Come and see the Huntley Middle School, Clinton Rosette Middle School production of Disney's Beauty and the Beast Jr., May 19th through 21st at HMS. See Miss Campbell, Mr. King, Mr. Boland, or Mr. Byers for more information.
You may now resume your regularly scheduled program. This has been a PSA brought to you by Mr. Bolin.
All right, letter B. The data in the table gives the value of a painting over time. Which kind of function best models this data? And we want to write an equation to model it. So, as we look at this, the first set of numbers, it looks like we're adding what? $160 there. For our second one, we're adding something. It's not 160. We're adding 168. For the second set, we are adding 176. So it's not going to be linear. Can we look at our second difference just with those three? Well, we've got a plus 8. We have a plus 8. Okay, maybe this could work. Well, let's try the next one. 3890 minus 3704 is 186. Well, now that second difference is 10. So it's not going to be quadratic.
Linear? Nope. Quadratic? Nope. What are we left with?
We're left with exponential. So to figure out what our common ratio is going to be, we're going to take the value of 1 year divided by the value of year 0 to find out what we're multiplying by each time. So 3360 divided by 3200 is going to give us 1.05. Okay, and we can double check this. If we multiply each one of these values by 1.05, we're going to get the next value in the chain. So now if we remember back to when we worked on exponents and we were writing things in exponential form, chapter 7, we put our starting value, year 0, $3,200, times our common ratio, 1.05, to the x power. And we can always double check and plug in some of this data and check and see if our answer is correct, and we will find that it is correct. Hope you guys enjoyed this lesson. We have a couple examples of fine art down there at the bottom, and we will see you all in class.